Chapter 8, Think and Explain. Number 56. While riding a carnival Ferris wheel, Sam Nasty horses around, climbs out of his chair along the spoke, so he's halfway to the axis. How does his rotational speed compare with that of his friends who remain in the chair? So this is, we talked about in class, so V equals R omega. And so the farther out you are, the greater the speed is, because you're traveling a bigger distance. And so Sam Nasty is not traveling as fast, doesn't have as large a linear speed as his friends do, but because the Ferris wheel is a rigid body, he has the same angular speed. So I guess the first part is compare rotational speeds. That stays the same. Tangential speed is bigger for the people on the outside. And why the answer is different? Because we're talking about two different things. And also V is related to omega by the radius. And imagine, I should really pin down the name of this thing. I call it something slightly different, I think, every time. But Whip the Dragon's Tail. You got a bunch of people standing in line, all holding hands. And then the first person in the middle just starts rotating slowly. The person on the outside has to run really fast. That's because the farther out you go, the faster you have to go in order to maintain the rigid body. 58. Use the equation V equals omega R, or R omega as they have here, to explain why the end of a fly swatter moves faster than your wrist when you swat a fly. Well, you got a pivot point right there. My mock fly swatter got a pivot point right here at the wrist, and so the farther out you go, the faster it's traveling, because my wrist, the hand, and the pen fly swatter move the exact same time, and just this has farther to travel, whereas this point right here just doesn't travel at all. 60. Flamingos are frequently seen standing on one leg with the other leg lifted. Is rotational inertia enhanced with the long legs? If you think about rotational inertia, it's always about some point, and usually if you think about something standing, for instance, let's go to our fly swatter now, flamingo, its pivot point is basically at the tips of my finger, right there. There we go, that's a little bit better. It's at the tip of my finger. If I sort of loosen up my grip a little bit, the thing is going to rotate down at the base. So moment of inertia, the more mass you have farther away, the greater rotational inertia. And so when the leg gets picked up, you're now shifting the center of mass up slightly, so it should increase the rotational inertia. What can you say about the bird's center of mass with respect to the foot on which it stands? I think we just did. They say it's rotational inertia enhanced. It is, and so with the greater rotational inertia, the harder it is to get going, the harder it is to sort of get it to start to wobble. The downside is that once it starts to sort of tip over, it's harder to stop it, but presumably they put their other foot down at that point. 63. A softball and basketball start from rest and roll down an incline. Which ball reaches the bottom first? Defend your answer. Now, this one's a little bit tricky because softballs, it depends on if its regulation is ball or not. Softballs tend to have stitching on them, and so I assume he's not thinking about that. He's just thinking about you have a solid ball and a hollow ball. And the distribution of mass for the hollow ball is more to the outside, and so therefore it has a greater relative rotational inertia. The amount of energy that starts out with all potential converts it into kinetic, part of kinetic to rotate it, part of the kinetic to take it down the ramp. And so if the ball is rolling down, higher percentage of the kinetic energy has to go into rotating the basketball, and so the softball should make it down first. 65. Can a force produce a torque when there is no lever arm? Can a force produce a torque when there is no lever arm? No. Because torque is the lever arm times the force. Now, if he's talking physically a lever arm, it's not necessarily, when you use a wrench, you don't call it a lever arm, you call it a wrench. So I don't think that's what he's talking about here. The other aspect is a force can, without a lever arm, a force can produce a torque of 0 Newton meters or whatever units you like. But again, I think what he's going for, the spirit of what he's going for is no. 79. Centers of gravity of the 3 trucks on the hill. If we can treat that the weight is acting at the center of gravity, and so the stability comes down to how much of the weight is acting basically around the pivot point. So you have the bottom tire. So this thing's on an incline right here. You got the bottom tire. When the center of gravity is on this side of it, it's like there is a torque trying to rotate the truck basically down the hill. If it is on the other side of the pivot point, so that point on the tire, it's trying to rotate it up the hill, which is stable. And so the first one at the bottom is going to tip over. The one in the middle, it looks like the distribution of weight is right over the tire, so it is barely balanced. If it is truly right over that tire, then it won't take much to tip it over, but it's not tipping over yet. And then in the one at the top, in the picture, you've got the farthest to the right for the moment arm, and so we should be stable there. 84, friction is needed for a car rounding a curve, but if the road is banked, friction may not be required. What then supplies the needed centripetal force? All right, so if the road's banked, the car is traveling around like this. The center of the circle is that way, not that way. This is not box on ramp. This is car going around banked curve. And banked just means you've got a slope there. So as it's going around, the center is that way, so the direction of the centripetal force is that way. Well, if you think about the forces acting on the car, you have weight acting down and you have normal force acting this way. Well, weight does not contribute to the force going in that direction. So what happens is that the normal force, part of the normal force is opposing the weight, and part of the normal force is this way. So the force that supplies the centripetal force is the horizontal component of the normal force. 85. Under what conditions could a fast-moving car remain on a banked track covered with slippery ice? If it's going the exact right speed, it should be able to take it. If it's, they say slippery ice, I'm assuming we're thinking about frictionless ramp here. This is very similar to the previous one in the fact that it is the horizontal component of the normal force which supplies a centripetal force, and there is an optimum speed for each angle or an optimum angle for each speed. If he drives, so let's say that it's a set angle and there's an optimum speed. So if he drives faster than that optimum speed, he will slide up to the top of the track or towards the outer part of the track. If he's driving slower than that, he will basically slide down the ramp as he goes around. 86, explain why centripetal force does not do work on a circularly moving object. And again, work is force dot product with the displacement. And so the force is towards the center, but the movement is perpendicular to that. So movement this way, force that way, assuming a circle going around like this. And because they are perpendicular to each other, there's no work done. And I think this relates to a question we have later on about the Earth. Maybe that's a different chapter. But if you think about if the Earth travels in a circle around the sun, it's not like it gets faster every time it goes around the sun. It's basically traveling the same speed as it goes. And if it did work, then there'd be a change in the kinetic energy, and because there's only one force pretty much acting on the sun, that's the force of gravity, which is a conservative force. So if work were being done by the gravitational force, then there'd be a change in kinetic energy. There'd be the speeding up or slowing down. It speeds up, the Earth moves farther away from the sun, slows down, the Earth would spiral into the sun. And so, again, assuming circular orbit, we'll get into some nuances in the later chapters. And that is it for the Think and Explain from Chapter 8.